Hi guys, this is Angela Galloway and I'm going to be covering Chapter 1 for Statistics, our Stat 220 class. In Chapter 1 and 2, we pretty much are just going to go over some basic ideas of statistics, learn some terminology that we'll be using throughout the semester, but overall we won't be doing a lot of actually calculating statistics yet. First, we have to understand what all the words mean before we can start calculating them. So in chapter 1 and 2, you really won't even need a calculator for the most part. We won't get into the calculating part until chapter 3 and 4. Now, one of the nice things about statistics, or at least the way our class is set up, is that really each chapter builds on each other. So even though this is chapter 1 material, we really will be discussing these terms that we talk about here all the way until our last chapter, chapter 10. So understanding these terms now is going to help you to do better in the rest of the class, because if you can understand what we're talking about now, even if it seems simple at this point, we're going to continue to build on some of these ideas. So try to really learn these and have them in your vocabulary so you'll understand them when we talk about them in later chapters. So one of the first things I do with my lecture classes on the first day is I kind of just put a blank screen up here and I say, what do you think of when you think of statistics? So different people are going to say different things. you know, some of them think of probability, maybe thinking of, betting or doing the odds of something or going to Vegas, that kind of stuff. Others think of statistics just anytime you see graphs and data. A lot of people are going to think of sports when they hear of statistics. So they'll think of, what's the player's stats, what's their 3-point percentage, or what's the quarterback ranking, that kind of stuff. And I know a lot of times when I'll tell people that I'm a statistician or whatever, the first thing they kind of think of is, oh, do you work with a sports team or something like that? And I'm like, no, it's not really that cool, to be working with a sports team, but I do get to work with numbers. But of course, sports teams, they are going to have statisticians there, but they're mainly going to be working with just descriptive statistics, and we'll talk more about that in these first two chapters. Another thing you might think of, something that's very appropriate right now, is thinking about polls. Since we have an election coming up this year, we are seeing a whole lot of polls, and we see a lot of polls in the media anyway, but we definitely are seeing them now as we're looking at this presidential race coming up. And so that might kind of be at the forefront of your mind when you think about statistics. So those are all things that we will cover somewhat in statistics. But of course, there is an actual definition for statistics, and the definition for statistics, it's the science of organizing and summarizing information to draw conclusions or answer questions. So the nice thing about this class, the reason why it's really my favorite to teach, is because it's so easy to apply what happens in real life to what we're learning in class. Now, that's not always the case in some math classes. Sometimes, I hear students say, when are we ever going to use this? Or, how is this going to apply to real life? And so sometimes that's hard to figure out, like if you're teaching a trig class or calculus class or even a college algebra, like when we're learning about the vertices or the vertexes. Of a parabola or whatever. It's kind of hard to say, yeah, you're gonna, be doing this every day. But with statistics, a lot of these things, even if you're not calculating them every day, you are possibly going to be needing to interpret these type of numbers every day. So some places you're going to see statistics in business, there's usually a whole forecasting department, or even like a quality control compartment or department. All those are going to be using statistics. And so before I was a teacher, I worked at Fruit of the Loom, which is here in Bowling Green, and I was a forecast analyst. And so what I did was I figured out, I forecasted how much underwear we were going to sell in the coming months and how much we needed to produce so we would have enough to ship to Walmart and Target and Kmart and all the different stores that were going to need that. And so I didn't just guess a number. I didn't just come in and say, yeah, I think they're going to need about 1,000 dozen. I obviously had to use some kind of data to forecast what was going to be needed based on what had happened in the past. And so that's going to be one place that business uses it. Also, talking about quality control, if you've ever worked in manufacturing or been around business recently, the Six Sigma um, idea has kind of been pretty heavily used in manufacturing now. And Six Sigma obviously has its basis in statistics, and you'll see that a little later. We'll probably reference that. But if you've gone through any Six Sigma training, I did some while I was at Fruit of the Loom. I did the green belt training for Six Sigma. And you'll notice that really it's just a statistics class that they're teaching you. It's just trying to think of it related to business. But it is going to be a very, applicable thing to the business world. Now, then we've got medical field and healthcare. You hear about clinical trials or experiments that are going on. Anytime they're trying to investigate a new drug or a new treatment, they have to go through some sort of clinical trial, right? And all that is done with statistics, and we will definitely be looking at some of that. In sports, we already talked about, we're going to hear some of those descriptive stats that describe how a player or a team is doing. And then the politics or media, we hear polls, a whole lot of stuff there. Knowing how to calculate stats is good, but I'd rather you understand and be able to explain the statistics more than just knowing how to calculate them. Because, like I said, are you going to be calculating these in everyday life? Maybe, maybe not. It depends on what field you're going into. If you are going into a math related field, then yeah, you might be calculating it. But if you're going to become a nurse or you're going to become a chef or you're going to become whatever, you might not be calculating statistics every day, but you might be reading journals that are talking about clinical trials and you want to know what those numbers mean. Or you might just be watching the news every night and you want to know where do they get those percentages, or is this a good or a bad number that you just want to know about. So I think being able to understand those and think critically about some of these polls or trials or experiments that you hear about will help you just be a more practical consumer of things. So the difference in math and stats that I have here, kind of just to explain, because I think when students start in this class, they're thinking, what am I going to learn in a stats class? Why am I taking another math class? Well, this math class is going to be a little different than what you would see like in your college algebra class. So, in your college algebra class, let's say if you just finished that, the answer to that, you may have done a problem and you come to the end and the answer is x equals 5 and you're good. That's it, right? You circle it and you say, I'm done. But in statistics, once we get that 5, then we start to ask questions about it. We start to say, well, why is it 5? Or what does a 5 mean? Is a 5 a good answer or is it a bad answer? How does it compare to other answers that we've gotten in the past? So we're going to be investigating those answers more after we get the answer. Instead of just saying, here's my answer, we need to interpret what that really means. Okay, so getting into some of the terms that we're going to be using, really most of these, you just need to go through, kind of think about what these terms mean, because as I said, we are going to be using them throughout the semester. So once I define what a parameter is here, I don't really go back and define it again, like I assume that once you've gotten through chapter 1, you now understand what a parameter is, and so we'll just use that in our normal speech. So we've got two types of statistics, two branches, I guess you'd say. We've got descriptive stats and inferential statistics. So descriptive stats is probably what you have been exposed to in the past if you've taken like just a basic stats class, or if you've had like a stats chapter in one of your math classes, this descriptive stats, we're talking about graphs, charts, tables, calculating averages, all that. All it does is just describe. Okay, so we're really just summarizing our information. Inferential statistics, of course, is going to be the higher level of stats, and that's what we're going to get into probably in the second half of the semester, where we start doing the inferential statistics. But what we do there is we're trying to infer something based on the data that we've got. Okay, so we're going to get some information from a sample, then we're going to try to infer something from that sample about the population. So to be able to understand that definition fully, we have to look at what do these words sample and population mean. Okay, so I think the easiest way to think about this is to kind of see this picture down here. And so I think I draw this probably about 100 times throughout the semester in my lecture class, just to reference back to, okay, remember, this is our sample, this is our population. So the population is the collection of all individuals that are under consideration in a statistical study. So for example, a population might be all of the US, okay? So it's going to be a large population, or all college students, or all female voters, or all whatever. Okay, so that's going to be our population. A parameter is a numerical summary of the population. So if we had, let's say we took a census, okay, and we were able to find some percentage from that census. A census goes out and collects data from all of the US, right? So that would be our entire population. And so then we could create a parameter from that population data. However, most of the time, we're not going to be able to go and get information from the entire population. For example, if we're talking about the election coming up, if they're trying to find what percentage of voters are going to vote for Donald Trump, okay, the percentage of voters they're looking for is they want to know, looking at all registered voters in America, how many are going to vote for Donald Trump, right? Well, how long would it take to go ask every single voter in the US who they're going to vote for? Well, by the time we collected that data, it would already be after the election, right? So instead of going and asking every single person, hey, who are you going to vote for? They instead take a sample, right? So they take a sample from the population. Now, we'll talk about later how we want that sample to be a good representation of the population. So you don't want to just go out and sample your 10 closest friends, right? You're going to get a sample that has a good mix of ages and genders and races and all that stuff, okay? But our sample is going to be smaller than our population, right? So our sample is going to be easier to collect data from than the population, because the population is huge. We probably aren't going to have the time or the money or the resources to go out and get information from all of them. So instead, we're going to take a sample, collect data from that sample, and then the data we get from there, we're going to create a statistic with. So that's what how we actually use the word statistic. A statistic is just a numerical summary of the sample. So we're looking at the data from the sample and then creating some statistic. That statistic could be a percentage, it could be a mean, it could be a median. You know, there's lots of statistics we can calculate. But for now, I just want you to think of, okay, we're taking that data and we're doing something with it. Now, in inferential statistics, what we do is we take that statistic and we infer about the parameter that would have come from the population, but we weren't able to get information from the entire population. So instead, we're just going to assume that our statistic is probably pretty close to what the true parameter is. Now, this is how they pretty much do all polls that you hear on the nightly news, okay? Because there they'll say 40% of registered voters are going to vote for Donald Trump, let's say. Now you might think, I'm a registered voter and I was not asked in this survey, so how do they know 40% of registered voters feel this way? Well, if let's say it's a Gallup poll. Gallup is one of the most respected polls out there because they do very good sampling, okay? Um, they usually take a sample size of about 1,200 people. So they go out, they randomly choose 1,200 people, they ask them, they get the data, They create a statistic. So let's say they got 40% of their sample said that they were going to vote for Donald Trump in this election. We then infer that this sample is probably a good reflection of the population. So if 40% of our sample is going to vote for Donald Trump, we're going to say about 40% of the whole population is going to vote for Donald Trump. And that's why you see different polls have different numbers, right? So some polls say 37% are going to vote for Donald Trump. Some say 35, some say 42. But hopefully we'll notice that they're all kind of centering around the same number. And we're going to talk a little bit about that later on, about how every sample is going to be a little different because they're all going to have some error. But overall, that's what inferential statistics is all about. It's about taking a sample and inferring something about the population, okay? So here's just a quick example, identifying the population, the sample, the parameter, and the statistic. Some more definitions that we have here. A variable is just a characteristic. We have two types of variables that we're going to talk about, qualitative and quantitative. Qualitative can also be called categorical, and it just puts people into groups or categories. So examples would be gender, race. If you have like a numerical scale, like how happy are you at your job on a scale of 1 to 10, that would technically be a categorical variable. Yes, no questions, all those would be qualitative categorical variables. Quantitative variables, from the word quantity, of course, we're thinking of numbers. So things like age, height, weight, time, etc. We are going to deal more with quantitative variables because, of course, if we want to calculate percentages or whatever, we kind of need numbers there, right? So most of the time we're going to have quantitative variables, but we are going to talk a little bit about how we could use statistics with our qualitative variables. Now the quantitative variables can be broken down two other ways as well. So we've got discrete and continuous variables that are types. Those are types of quantitative variables. So a discrete variable is a quantitative variable whose possible values can be listed or counted. So I think the main thing you want to think of there is counted. So if you can think of a count of something, like if I tell you to choose 3 cards from a deck and then I ask you how many of those cards are face cards, you would give me a number from 0 to 3, right? So it would be 1 card is, or 2 cards. You wouldn't say 1.5 cards were face cards, right? You would have a count of them. How many years have you been in school? That would be a count. However, continuous variables are more than just a count. They could really be anywhere on the number line. So if we're thinking about the number line here, we'll just say we start at 0, okay? So if I'm thinking of weight, I could pick any point on this line, and that could possibly be somebody's weight, right? So it could be 150, right, which would be a whole number, or it could be like 150.1 or 150.12, right, just depending on how accurate our measuring utensil is or instrument is, then we could get it pretty accurate, right? Several decimal places or whatever. So it doesn't just have to be a count, okay? It could be any point on the number line. So those things are like weight, height, length, and time. And the difference in these two variables, why we break them down, is because we're actually going to deal with them differently when we get into looking at different distributions of the data. And so we'll be talking about this, we'll be talking about discrete variables when we get in chapter 5 and 6, and continuous variables in chapter 7 through the end of the semester. Okay, so different types of studies or different ways to collect data. We could use observational studies, or we could use some sort of designed experiment. An observational study, we just observe, okay? That probably makes sense, right? We observe in an observational study. So sample surveys, polls, all those, we're just observing characteristics. So we just go out and say, you know, we ask them something, or we look at them and say, do you have blue eyes? Yes or no? Okay. We're just observing. We're not doing anything to give them blue eyes. We are just asking if they have blue eyes. In a designed experiment, we're imposing treatments on people. So if we were to say, give them a certain medicine that we think will change their eyes to blue, and then we see if we get those results or not. Okay, that would be imposing a treatment on somebody. So experiments, you are imposing sort of treatment. Observational studies, we're just asking a question and just collecting data. So if we're trying to establish causation, okay, if we're trying to say that one thing caused something else to happen, then we really need to use an experiment instead of an observational study. The reason why we can't use observational studies to establish causation is because we have something called confounding. And so this is going to occur in a study when the effects of two or more explanatory variables are not separated. Therefore, any relation that may exist between an explanatory variable and the response variable may be due to some other variable or variables not accounted for in the study. So we'll talk a little more about this later on, but for now, just kind of think about that we need to use an experiment if we're going to prove one thing caused another, okay? A lurking variable is something that was not considered in the study, but that it affects the value of the response variable in the study. So experiments, when we set them up, when we put people into treatment groups, we can uh, kind of control some of those lurking variables, okay? We can't do that in an observational study. So I say here, for that reason, we would like to always use designed experiments, but why would this not always be possible? And so we said it might be impossible to do an experiment or to obtain the data, like maybe if we're looking something in the past, we're just able to collect the data. We can't really, impose any treatments on them. Or it could be unethical. So one of the examples we'll talk about in class is maybe texting while driving. I might not want to actually do a real experiment on the highway of that, right? I don't think I'd want to put anybody in a group and say, okay, this group is going to go text at 5 p.m. down the main road of the town and see, if they have a wreck or not. That wouldn't really be ethical to do that. So you wouldn't want to do that, or if you had a drug or something that you knew caused problems, like for example smoking and pregnancy. We kind of have enough information now to know that that's not a good thing, but if we were wanting to do an experiment, we probably wouldn't want to force mothers to smoke while they were pregnant, right? Because we realize that could have adverse effects on the baby. So we have to do ethical experiments. Once we notice that there is a negative reaction occurring, we need to stop that experiment. So instead, we need to figure out ways that we can maybe do those as observational studies instead of doing them as experiments. So here's an example kind of to show how you can come up with funny situations if you're just looking at observational studies. Okay, so this is an observational study, and this is an actual paper, and it says new evidence for the theory of the stork. And of course, the people that did this knew that the data was just kind of comical. They know that the stork does not really bring babies, but it was just to show you that in this simple way, that using an observational study can make you come up with inaccurate results. Okay, so here we're looking for, or they're looking at this was years here. So we're looking at the number of out of the hospital deliveries and the number of the pairs of storks. And so you notice that as out of hospital deliveries went up, the number of the pairs of storks went up as well. So you might say that it looks like the more storks there are, the more babies are being born out of the hospitals. So therefore, maybe the babies are being brought by the storks, right? So we've got the data right here to tell us that, so I think we've come to our conclusion, right? Well, obviously we can't show that because we all know that babies do not come from the stork, right? So we know that there has to be another answer here. Something else is going on in the background. And so what's going on in the background is those lurking variables or the confounding that's happening. Something is happening that's causing both of these numbers to go up. And so really what happened here was, and this was in Germany, what was happening here was something similar to what has been happening in our in the US, we've been seeing more people kind of going to the out of hospital births, wanting to do the home births. That's kind of become a new trend that we're seeing. And so that was happening there as well. And then the same time, the storks were living in a certain area where they were starting to preserve that wildlife area. They were wanting to preserve the wetlands that the storks lived in. So they were doing that at the same time. So the stork population was going up at the same time that the home births was going up. Now they really had nothing to do with each other, and there were two different explanatory variables affecting these response variables there. But if you just put two things together, you might see that you get these what looks like associations between two things when they really aren't there. But what I want you to think about is looking at these, it's kind of a funny situation, right? But there's other situations that it can be a little harder for us to identify. Are these things really causing each other to happen, or is there some confounding going on? So, one of the big topics that we've heard a lot about in recent years is vaccines and autism, right? So, they'll show some data on how vaccine use goes up and so does autism rates. But we have to think about, is there really any experiment showing that one caused the other to happen? And there is no data that shows that there is a correlation between those two when looking at experimental data. Okay, when all the outside effects are taken out, there is no association between the two. Okay, there was a huge study done last year, I think maybe 200,000. It was a very large sample size. And they saw that there was no reason to believe that the vaccines are causing autism. However, there was one study done a long time ago that did show some correlation. The problem with that study was that it was a very small sample size, and that study has never been able to be replicated again. They have never been able to get those same results again. So it kind of shows that that study really was just an outlier, was not a good study there. But we're still going to hear things like vaccine rates are going up and autism rates are going up. Well, why are vaccine rates going up? Why are more children being vaccinated? Because of the wider availability of health care, right? So more children are getting vaccinated. Why are autism rates going up? Well, probably for the same reason. More children are going to doctors and maybe being identified as autistic. Now, are more children autistic now than were 100 years ago? Well, I don't know, because 100 years ago we had a very, I don't even know if they had the same definition for autism. Probably the only people that were identified as autistic or having some sort of special needs were those that were on the very far end of the spectrum. Now we have a very wide spectrum where we can say kids that are just, a little socially inept, maybe on the lower end of the spectrum. And then we've got kids all the way up to the higher end of the autism spectrum. And so more kids are just being diagnosed as that. Does that necessarily mean that one is causing the other? Well, so far we haven't had proof of that. But that is something that is kind of difficult for some people to disprove when they see graphs that show autism rates increasing at the same time vaccination rates are increasing. So you want to just be leery of some of those. Some of that data that you see that's just been collected observationally, that hasn't been collected by doing an experiment. So some of the ways that we will collect data is what we're going to talk about in 1.3. That's simple random sampling. And so we want to collect data randomly. Like I said, we don't want to just go out and collect data from our 10 best friends, right? We want to get a good representation of the entire population that we're interested in. So all these are talking about collecting data and how we're going to do that. Now, the way your book talks about using it, using the random number chart, it's on page 25 if you look at your ebook, or it's in table 1. Also, usually when you're doing this on a homework assignment, there's a little box that'll pop up that you'll click on, and that will have the random number table there. But the way that they tell you to look at it is they'll tell you a certain line number and column number to go to. So let's say it said go to line 01 and start at column 18. So we would be right here at the 8, okay? And so we would start down here. We start at this first number, and we would use 2-digit numbers, because you'll notice when these are numbered, if I have more than 10 people, I'm going to need 2 digits, okay? So I've got 2-digit numbers here, 01 up to 24. So I would start here and I would have 86. So 86 is not anybody up here, so I would not choose 86. 50, that's not a number. 97, I don't have a 97. 73, nope. 74, nope. Now I'm going back up here. 08, oh, I do have an 08, so Lexi gets chosen. Then 15, I have a 15, so that's Mike up here. 85, I don't have that. I go back up again, and I'm at 14. So these spaces here really mean nothing. They're only there to help you read the numbers, because if they were all just in a straight line, it would be kind of hard. It'd be easy to lose your place. So 1-4 is 14, and so that would be Sarah there, and so those would be the 3 people that we would choose. So that is how you are going to use your random number chart there. So here's some information about polls, if you want to look at that. Some other sampling methods we have there, just different ways of sampling. Here's some more information on experimental design. These are all things you can read through. I don't think it's anything too difficult. Of course, if you have any questions, you can always ask me about them. But I think once you read through it, look through the books, do some of the homework exercises, you'll pretty much get the gist of what's going on. So again, if you have any questions, you can click the Ask My Instructor on the My Stat Lab, and it'll send an email to me, or you can just email me directly at angela.galloway@kctcs.edu. Thanks.